So we were on IEEE 802. IEEE 802 means all standards, almost all local area standards developed by IEEE. That includes Wi-Fi, that includes Ethernet, that includes the token ring, and there are many others up to 21, 8, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 21, 23. I think they're up to 23 right now. Anyway, all of them use this address, 48-bit, which is used with the colon marks. And when you go to IEEE, they give you 22 bits. And so you get 2 raised to 22 addresses for $1,000. And then you can start assigning from 0, 1, 2, 3, 4, 5 all the way to whatever number you want. The first 2 bits are reserved. The first 2 bits are, the first bit is for individual or group. If it is 1, that means it is a multicast address. And those are again assigned by IEEE. And so for example, to all the bridges, you want to send a message to all the bridges, there is a particular multicast address. You want to send it to all routers, there is a multicast address. To all DHCP server, there is a multicast address. So there are multicast addresses for many different functions. So that they will all have one first bit equal to 1. Second bit is universal or local. 0 means universal, 1 means local. 0 means individual, 1 means group. So if that bit, second bit is 0, that means it is globally unique and assigned by IEEE. If that bit is 1, that means it is locally assigned by the manager of that building and it has no global meaning. So that OUI, everything else is meaningless if that second bit is 1. Alright? And at that time when we were doing this Ethernet addresses, some people really wanted the addresses to indicate location. They wanted it to indicate the building number, the floor number, and the closet number. So they said, okay, you can do that as long as you put this bit 1 and then you can put whatever you want in the rest of the bits. Right? Those things are all gone. We no longer use any location in the addresses. Those were demands of the day, but they really failed. So these are unique. Basically, we use globally unique, which means this bit should always be 0. Now, the only exception is the broadcast address. Broadcast address is all 1s. The first bit is 1 means what? It's a multicast address, it's a group address. The second bit is 1 means, but it is not. Second bit is 1, that's an exception, it is a universally multicast address. So basically that, as long as all bits are 1, that is a broadcast address, everybody is supposed to listen to it in every place. Is that clear? So it's not a local address. Broadcast address is not a local address, it's a universal address, but that bit is 1. It's very easy to check for all 1s than to check for all 1. Alright, now bridges. So the way Ethernet initially connected was that you had this wire and everybody tapped onto the wire, and then if you wanted to connect 2 wires, you put a bridge in between, and the bridge will listen to all the traffic on this side, and then it will, by listening to the traffic, it will understand who is on this side. Similarly, listening to the traffic and looking at the source address, it will know who is on this side, and when it saw a packet going to a station which is on that side, it will pick up and then send it over. So the bridges are called self-learning. Self-learning means they learn, they become smart just by looking at the traffic. You don't have to program them, telling them where the routes are, where the things are. Okay? And you, please close the computer. Alright? So, the bridges are self-learning bridges, and they learn by how they learn the location. Anybody? Yeah.
When they receive a packet from one side, they know that that router is on that side.
Yeah, the source address. They look at the source address and they make a note of it. So all the addresses are put into a table that you see on the source addresses. So then you know in this big table who is on which side. So bridges, they monitor all frames on LAN A pick up the frames that are for the stations on the other side, retransmit the frames on the other side, knows or learn about the addresses, and that is why we are self addresses. They make no modification to the frames. So they don't put their address as the source address. Even though they are transmitting on the other side, the source address is still the same as before. Okay, so no modification. They are totally invisible. Provide storage for frames to be forwarded. If the other side is busy, they will keep it in the queue. Improves the reliability because now you have less nodes per wire. Improves the performance because you have less collisions, and improves the security because you can prevent the traffic from entering a particular wire, and may provide flow and congestion control. So again, this was a debate at the time when we were discussing the standard. Some people wanted bridges to do flow and congestion control. So IEEE standard allows that, but nobody uses it today. Yeah.
So it's the same as switches in the book.
Now, is the bridges same as the switches in the book? So I'm coming to that in a minute. Next slide. So there are many things that we use. We use the word repeater, hub, bridge, router, switches. All right. So let me explain. So yeah, your question was whether bridges are same as switches. The answer is yes. In the beginning there was a slight difference, but now we said bridges were 2 ports, switches were multi-port, but now we don't, because there are no bridges left actually, only switches left. So we use switches. So repeater, what is a repeater? Repeater is a physical layer device. What is a physical layer? Physical layer doesn't really know the packets, it doesn't know the frames, it doesn't know all it knows is bits. A bit in is a bit out. That's a physical layer. So if you have an amplifier, a digital amplifier which takes a 1 and sends out a 1, it takes a bad one and sends out a good one. You know what is a bad one and what is a good one? A bad one is all crooked, a good one is very square. Alright, that is a repeater. So it's a 5-layer device. Hub is a multi-port repeater. So if you put a hub, you can connect many things. One bit comes in, one bit goes out. A bad bit comes in, a good bit goes out. That's a hub. You cannot buy a hub these days, but 10 years ago you could buy a hub which looks almost like a switch. You connect 10 computers to it. But the difference is basically it's a physical layer device. It doesn't do anything. A bit comes in, a bit goes out. If 2 people send a bit, both people's bits get mixed up, collide, and the collision is sent out. It doesn't do anything. It doesn't send jam, it doesn't send anything, but the 2 stations will collide and they will send out a jam, and these jams will come in and the hub will send it out. It's a physical layer device. That's a hub. Now this is not very clear in the book, so please listen carefully. Bridge or a switch is a layer 2 device. Layer 2, the difference between layer 1 and layer 2 is layer 1 knows bits, layer 2 knows frames. Layer 2 knows frames, it can calculate CRC, it knows a bad frame from a good frame. Layer 1 doesn't know a half frame from a full frame, doesn't know the beginning of a frame or the end of the frame. It knows only bits. Right? Everybody knows the difference between layer 1 and layer 2. Layer 1 is a bit level device, layer 2 is a frame level device. So the bridges look at the whole frame. If the frame is good, they look at the destination address and the source address. If the frame is no good, they throw it away. Alright? That's what we call a switch today. Collision doesn't pass through. If they see a collision, that's not a frame. Collision happens only on one side of the switch. It doesn't go to the other side. If it is a hub, the collision will go to all the hubs. So hub actually basically extends a wire. If you connect 2000 stations to a hub, what will happen? What will go up too much if you connect 2000 stations to a hub? Collision. Lots of collision. If you connect 2000 stations to a switch, the collisions will not go. But what will go is the broadcast. If somebody sends a broadcast frame from this side, it will go to all the other people because this is a complete frame, CRC passes, it's a multicast frame, it will broadcast to all the sides. So to stop that, we need a new device which is called a router. Router is a layer 3 device. Router is a layer 3 device. It doesn't it only looks at the layer 3 addresses to begin with, means it looks at the IP addresses, not the MAC addresses. But it also, because the broadcast frames do not have an IP address unless they have IP multicast, Ethernet multicast will not get through. Right? Ethernet broadcast will not get through. And so they stop the broadcast storms. If you put the whole campus on one LAN, on one Ethernet, there will be broadcast storm. Somebody sends out one broadcast and then the whole, it makes 50,000 copies are made, and somebody sends out another one, another 50,000 copies are made. There will be lots of broadcast, right? So broadcast is stopped by the router. So everybody should understand the difference between a repeater and a hub, a switch and a router. When you go to buy, if it says switch, and you go to buy to Best Buy or Walmart or whatever, a switch, that's a layer 2 device. It doesn't know IP. All right? It cannot. If you go to buy a router, it's a layer 3 device. It will probably have a built-in DSCP server and other things nowadays. They make NAT and so on and so forth, everything in there, right? That's a router. That's the difference between router and a bridge. Bridge are very cheap. For $5 you can find a megabit or a gigabit switch. $10. Routers are expensive. For $50 you can find a 10 megabit router. A gigabit router probably is $100. Yeah, go ahead. Yeah, $1,000. Huh? Hub and, okay, so again one more time. Hub and the repeater are layer 1. Repeater is just 2 port. Hub is multi-port. Right? So here is a picture here. Hub. So we connected these 3 nodes by hub and these 3 nodes by hub, and we connected these 2 hubs. This whole thing is what we call one collision domain. Anybody in this domain, when they speak, they can collide with the other person in that domain. But they will not collide with the people on this side, because these are connected by a bridge. A bridge bounds a collision domain, but the broadcast, it doesn't bound the broadcast. Right? A router bounds the broadcast domain. So this is called a LAN, and this is called an extended LAN. Because as far as the router is concerned, this is still one subnet. Right? So this is called extended LAN, and this is a LAN, this is an extended LAN. An extended LAN is one broadcast domain, a LAN is one collision domain. Now, so today we don't have hubs. So basically what happens today is, basically there are no collisions whatsoever. All this theory that we taught you about CSMA-CD doesn't really used in the latest devices. In the older devices it is used. So every computer has to implement it. It is implemented in every computer, but nowadays we connect our computer directly to the switch, and there is only 2 nodes on that network, on that LAN, in that collision domain. There are only 2 nodes, the switch and you. And you do not collide because there are 8 wires, 4 are used by you and 4 by the other side. So the continuously traffic can flow full duplex on today's switches. Today's switches are full duplex, and so there are no collisions, there is no CSMA-CD, there is no limit of 2.5 kilometers, and everything that we taught you about Ethernet is for the old devices. And the irony is that everybody has to implement all that old stuff, because you could have one computer in the whole building which has that old Ethernet, and they want to make sure that it also talks to everybody else. So everybody implements CSMA-CD, everybody has this collision detection, jamming, and back off and everything. So everybody understands how these things have changed? All right. Now that slide is not in the book, so make sure that you understand that. And that is a fundamental thing, and I want to make sure that that will be in the final exam. Okay. Next thing is ARP. Okay, so now you understand all the devices. That answers your questions about what is a switch, right? So it's a bridge. All right, now ARP. So we use the word ARP. Basically, there is a mixture here. Some packets come in and they are coming with the IP addresses, but when we send them on Ethernet, we have to know the Ethernet address, right? So how do you find out whose IP address is whose Ethernet address, right? And for that, there is a protocol called address resolution protocol. So given one address, you can find the other. Given the IP address, you can find the Ethernet address. Given the Ethernet address, you can find the IP address. And the protocol is very simple. You just ask, you broadcast a request. You broadcast what is the MAC address of this IP address. All right? And somebody who knows the answer will say the MAC address for this IP address is this. Done. Once you know the MAC address, then you just send the packet which was for that IP address to that MAC address. It will go to Ethernet. On the Ethernet, bridges will send it to the right place, and the right host will pick it up and open the packet and find the IP packet inside the Ethernet. Yeah.
Could this be vulnerable to an attack where you've got a...
Yeah. Clearly, so there is an ARP poisoning, and there is all kinds of ARP attacks where you could say, well, I am X and I am Y, I am the president, I am the bridge, I am the router, whatever you want to be, you can be. Right? You could be any IP address you want, and the packets will be sent to you, and then the other guy will be left into a black hole. And so there are attacks. The only reason it works is because this is all done inside a LAN. So another definition of LAN is single domain of ownership. All the people whose computer are on this LAN, they somehow belong to one company. Right? So they are not going to play games like that. Hopefully they will, otherwise will be fired or something like that. So that's why it works. Okay, that's all I'm going to say about ARP. Now, ARP answer can be given by anybody. It doesn't have to be the host. Routers give most of the answer most of the time. Yeah.
What if different answers are given by different?
Yeah, obviously then you are in trouble, because then then one person is wrong.
I mean, like, what if, does it send it to the first one it gets, or?
No. See, thing is, here's the thing. You broadcast your request, the response comes back to you, right? And if you get a response, you probably are going to use it. You're not going to wait for the second one. Now, later on, second one comes. I think what will happen is most likely you will override the previous response, and now you will start sending the new one. I mean, there is no other method, because you might have changed your MAC or IP or something, who knows. And these addresses can change. The thing is, your MAC address never changes, but IP addresses change. You take this computer, it has an IP address, take it outside, there's a different IP address. Okay? All right. That brings us to the end of Ethernet and ARP. And Ethernet and ARP. So these are the four key conclusions. First is CSMA-CD, means carrier sense, means listen. Multiple access means share. And CD means listen while transmitting. So listen while transmitting and stop on collision. That is what collision detection is. And use a truncated binary backoff. So what is binary? Why it is called binary? The backoff range goes up by a factor of 2 every time. And why it is truncated? You stop of 10. After 10 attempts. You have 16 attempts total, but after 10 attempts, the backup range doesn't go up. Ethernet uses 48-bit addresses. First bit is unicast multicast. Second bit is universal. 22 bits are OUI. OUI, IOU. You know what is OUI. OUI is organizationally unique identifier. That tells you the manufacturer of that equipment. You can look at any iPhone, you can look at any computer, you can look at any device. You can figure out who made it by looking at the Ethernet address. Okay. ARP. ARP is used to find the MAC address for a given IP address and vice versa. Any questions?
When you say vice versa,
Yeah, so given a MAC address, you can find what is your IP address.
there's always, there could be some multiple IP addresses or just one?
Oh, one MAC, okay, that's a good question. I think only one IP address for that interface. All right, so this is all up to this. You see, we are especially asking you to skip those problems. We didn't cover them. We covered this section and this pages. All right, the homework. Homework is suppose A and B are on the same 10 megabit Ethernet bus. The propagation delay is 325 bit times. A begins transmitting, and before it finishes, B begins transmitting. Can A finish transmitting before B is transmitted? Now, on Ethernet, the minimum frame size is 512 bits. Right? So, if the distance is 325 bit, I don't think that's the problem. Why or why not? In the worst case, when does B signal reach A? And the minimum frame size is actually 512 plus 64 bit. The 64 bit is the intergap time. You know, basically you keep onto the medium for 64 more bits after you transmit the frame. Okay, so that's the homework. The next thing I want to do is VLANs, PPP, and MPLS. Okay, so what is a VLAN? Actually, what is a LAN? LAN we talked about is an extended LAN is actually is a broadcast domain. So here you think no. Okay, let me correct myself. So we introduced the term LAN and extended LAN. Now the word extended LAN is gone. Somehow so in the beginning when the bridges were just new thing, we distinguished between LAN and extended LAN. Now everything is a LAN. All right. So basically a LAN is a broadcast domain. So this whole thing is one LAN up to here. When the router comes in, the LAN ends. All right. So there are two LANs here because there is a router. There are two LANs. This is one LAN, and then there is something on this side. In this picture, there are two LANs, right? So we will not use the word extended LAN anymore. For simplicity, we'll just call them LAN. And so single broadcast domain is one subnet, or a subnet is a LAN. So no routing between the members of a LAN. If you want to go talk from here to there, you don't use IP at all. You don't need IP at all. You can just send in MAC frame and then it will go there fast and everything is done. So you can talk Ethernet. So we speak the same language. We just use that Ethernet address and we can talk on this side. But if I want to talk to other side, I need the IP addresses. So we need a router. Right? So that is the definition of a LAN. A LAN is an Ethernet broadcast domain, and when we want to talk to somebody on the LAN, we don't need IP. We can just do with Ethernet addresses. We can send messages. But we want to go and go to other LAN, which is not in the same broadcast domain. We have to go through the router, and the routers only understand the IP addresses, and therefore I have to get an IP address of the other side. Yeah, go ahead. Yeah, link local addresses. This is a link. Now hold on. Link local addresses that's a good question actually, and I'm thinking about the answer myself. Link local. This could be whole thing could be one link, because what is happening is with the link local address, when you decide to get an address, what you do is and this is an IP address. Right? You say, well, I'm selecting this IP address. Is anybody else have that address? That's a broadcast message. It will be sent to all of these people. And if somebody else has it, you won't get it. If nobody has it, you can use that. So the whole thing is one link, not two links.
So you're communicating with the other people on the link?
Yeah, so you can communicate with other people on the same link using link local addresses. If you want to talk to them IP for some reason, yeah. So here's the reason. I'll tell you why you need IP though. Maybe I may confuse you a little bit. Let's say you want to do file transfer protocol. FTP. You cannot do FTP without going through IP, because FTP requires TCP. TCP requires IP. You understand? So even if two stations are the same, this server and this client want to do FTP, they will, because the protocol is designed so that they need IP. But you could design a protocol, and there were lots of protocol design in the original days of Ethernet which did not need IP. And so I could transfer a file between these two, but I will have to design a new protocol which doesn't use TCP IP. You see what I mean? So with the current protocol that we have, they need the whole stack. But one can always line. So there are many protocols. And where is Azin? Azin said, well, IP is a routed protocol. Basically, there are protocols which are not routed, which only stay on one side of the router. And one of the example is LAT, local area terminals. With the local area terminals, I can talk to my server in the local area, but not to the other server outside. And why they develop LAT? Because in those days the network was so slow. If you went beyond the router, your key will not feel very good. I mean, the keys will take time to get echoed. So LAT was very fast. And so they have lots of protocols that do not require IP. They will work on one side. Yeah.
The link layer address, the MAC address?
Yes. Link layer address is called MAC address, also called LAN address, also called 802 address. They're all same thing. Alright, so now we understand that this is one LAN, two LANs here. Now, what if people said that what if I have multiple departments and I don't want one department to see any traffic of the other department? So you have an engineering department, you have a marketing department, you have a manufacturing department, you have accounting, and accounting has everybody's salaries, data, and they are talking to each other. They don't want any people to be snooping on their traffic. Right? So they said, let's have virtual LANs. So virtual LAN means that these people, when they broadcast, their broadcast will not be sent to these other people. This switch is smart enough to know that this is one LAN, this is second LAN, and this is third virtual LAN. Virtual LAN. Really, in reality, they are all one LAN, but by management, they have been divided into 3 virtual LANs. Right? Having one home, for example, and making 3 apartments out of it. So people in one apartment cannot go into the other apartment, things like that, right? So that is the situation. So the switches are smart enough, saying that this port traffic will not go to that port. So that is called virtual LAN. And if you want to go there, from one LAN to the next LAN, you need a router. So if you want to go from this subnet, so this is one subnet, this is second subnet, this is third subnet. If you want to go from that subnet to that subnet, you go to the router here, and then you go like that. So this is a one-armed router. One-armed router means it has only one port, not 2 ports even. Everything comes in and goes out the same door. Okay? So, and that is because these are 2 different LANs, 2 different subnets. So each virtual LAN is a subnet, and therefore you need a router. And so you put a router, and then it will take it packets from here, change the IP. I mean, basically send it to the right IP subnet, and so on. The broadcast will not go through. Yeah.
That router also has only one IP?
Now it might have 2 subnets, means it might have 2 IP. It has 2 so basically one physical interface but 3 virtual interfaces.
One MAC interface, right?
And now that's a question. I have to think about that. I mean, it could probably have 3, but 1 is fine for the time being. I will have a problem with 3. Actually, 1, because the problem is if somebody opt it, And somebody says, what is the MAC address for this IP address? Then that is the answer. What is the? Yeah, I think we will need three MAC addresses as well. Any other question? All right. So basically what we did was we took a number of hosts and put them into three groups as shown in the previous example, a blue group, a red group and a green group, because this is one department, this is second department, this is third department, and they look like they are connected by wire like that, even though they are all connected together, but physically we have broken the connections. So the manager decides who is on what LAN, who is red, who is blue, who is green, and that's why it is called virtual. So why do you want to do virtual LANs? Because virtual is better than the real, believe it or not. Anything. You know, nowadays we do everything on the internet, and everything on the internet is better than the real. Shopping, entertainment, everything, right? So virtual is better than the real. The reason is because it is location independent. The marketing people don't have to be on that campus. They could be here and be in the part of marketing, right? Users can move but not change the LAN. Traffic between the LANs, you could move you were in the engineering department and go to the chemistry department. Well, engineering and chemistry, maybe not a good example. Engineering, and you wanted to go to medical school, you could go to that one but stay here. So traffic between LANs is routed, better to keep all the traffic on one LAN. Switch when you can, route when you must. So routing is generally avoided, and that's why we try to use the LAN as much as possible. It also provides better security. So VLANs are good and they are wildly successful. So there are lots of VLANs. So there are three types of VLANs: layer 1, layer 2, layer 3. And I am again not sure that book goes into all this different extent, but if I cover a topic, I really need to cover all this. So I am just going to finish it with three LANs. Layer 1 is one which basically physical ports like this. Basically every switch knows that port 1 is LAN 1, port 2 is LAN 2, port 3 is LAN 3, and so on and so forth. By everybody on that physical port is on one LAN. So every switch will have a port like this. Port A1 is on LAN 1, port A2 is on LAN 2, port A3 on LAN 1, and so on and so forth. That was layer 1 VLAN. That was the beginning of the VLAN world. Soon we realized that that's not really good because people can move from one port to the next. What do we do? So then we said, okay, we'll have layer 2 VLANs where we remember the Ethernet addresses. So this is VLAN 1 Ethernet address, this is VLAN 2 Ethernet addresses, and this became very, very complicated for the managers because managers cannot remember anybody's MAC addresses, and so they had difficulty keeping track of all this. So that went on for some time. Then they come to LAN 3. Layer 3 VLANs. In the layer 3 VLAN, they said every subnet is in a VLAN, and so therefore once you get the IP address, then whatever IP address you got, that VLAN you are on. Alright? So when we gave you the IP address, that time we checked out everything. You gave your MAC address and you gave your name and you gave your password and everything else, and we said, okay, you are marketing. You get the marketing IP address. Once you get the marketing IP address, you are in the marketing VLAN. That is called layer 3 VLAN. Huh?
Does that mean the IPs are assigned manually?
Well, I mean, it could be either way. You could be assigned manually, but it could be assigned DSCP.
Then we moved.
Yeah, when you move, then basically somewhere they will know that this MAC address is.
Isn't that more like?
So there is a mixture here. I mean, somewhere somebody has to really tell you whether you are part of this VLAN or not. So that's how it is. So basically, right now this is the one. Layer 3 VLANs are very popular. And so once you get the IP subnet, then you are on that VLAN. And it could be marketing department, it could be just an area. For example, this building could be one VLAN.
People sitting in the same room, how would that work? Or on the same
Yeah, no, so VLAN means that you share the broadcast. I mean, basically you have the broadcast in that LAN and you can see each other's traffic. Yeah. What we think of VLAN and VPN. So VPN is virtual private network. It has more to do with the security. When you connect to the company or connect to the university from a remote location, you don't want anybody on the way to see the traffic. You encrypt it and you send it. That is called a VPN. And that will be, if we discuss it, it will be discussed in chapter 8 or something like that. There is security. But there is no security issue here. Nothing is encrypted here in VLANs. Everything is clear and open, except that the question is who can see your traffic, who can see the broadcast and multicast. And that is VLAN members can see. All right. Now, I think that would be a good point to stop. And next time when we come in, we will talk about PPP.